Okay, this is the first of the real lectures in the course. So this is the start of Chapter 1, Introduction, and specifically it's an introduction to differential equations. And much of this introduction is going to be based on an old textbook by Murray Spiegel, Applied Differential Equations, specifically the second edition by Prentice Hall from back in 1967. It just has a good assortment of examples that gives you a good idea of what differential equations are, how they arise, and some of the methods that are used to solve them. So, as we said when looking over the course outline, a differential equation is an equation that contains not only variables but derivatives of those variables with respect to some independent variable. So, a good first example is that of a variable x, which represents some quantity that grows at a constant percentage rate. So this might be the balance in a bank account, for instance, or something like, say, a population of some species. In a case where resources are abundant, so there's plenty of food and shelter available. In such a case, you might expect that if the variable x represents the size of that population, then the rate of change of the population would be directly proportional to the size of the population itself. So let's take the case here. A is just a constant. So in fact, this differential equation, which relates the variable x to its first derivative with respect to t, this is an example of the main class of differential equations that we'll be looking at in the course. That is, it's an example of a linear differential equation with constant coefficients, because this a is just a real number. And let's take the case where a is a positive real number. That's why I describe this as modeling growth. Okay. So in this case, our independent variable is t. And we normally use the symbol t when we want our independent variable to represent time. So indeed, dx by dt is the rate of change of the variable x. And x could be something like a bank balance, or say the population of some species. Growing in some habitat, let's say. As is mentioned in the notes, x might also represent gross domestic product. We normally seem to expect GDP to grow at a constant percentage rate, say somewhere between 2 and 3% maybe. In that case, we would expect GDP to obey an equation something like this. So, what kinds of functions? So if we want to solve this differential equation, that means we want to find the value of x as a function of time in such a way that this equation is satisfied. So how might we go about doing that? Well, in this case, it's relatively simple. What we can do is take the x, this x on the right-hand side here, divide through by x, and then we'll take the dt over to the right-hand side. So in other words, we will, if you like, rewrite the equation as follows. Dx over x equals a dt. Now we've got all the x's on the left-hand side and the t on the right-hand side, so we can just integrate both sides of the equation. And that makes this equation a particularly easy one to solve. We can't always do that and do this, but in the case of this particular equation, we can. So if that's the case, then the integral of dx over x must be the integral of a dt. Now we're using indefinite integrals here, so the integral of x dx over x will be ln x plus some constant of integration c1. The integral of a dt will be at plus another constant of integration, say a2. Okay. So in other words, we can write ln x equals at plus a constant c3, where c3 is c2 minus c1. Okay. And now to make things more explicit, we can just use exponentiation. So this means e to the ln x, or x, is equal to e to the power at plus c3, or in other words, x is equal to some constant c e to the at, where c is just e raised to the power of our earlier constant c3. So this is something that in future you should recognize right away when you see this famous equation, a differential equation that we encounter quite often, dx by dt equals ax. The solutions of that differential equation are simply exponentials. X equals c e to the at. Okay? But this c is really just an arbitrary constant. So there are infinitely many solutions of this differential equation. In mathematics, often we like to know when there exist unique solutions of equations. So it's clear that we need to add further conditions in order to get a unique solution. And in this case, what we can do is simply note that if we set t equal to 0, this exponential simply becomes 1. So c is going to be the value that our variable x takes on when t equals 0. So this implies that x of 0 is equal to c. Or in other words, plugging this back into our original solution, x of t is equal to x of 0 times e to the at. So if we specify the value that x takes at time t equals 0, we get a unique solution. Okay. We call x of 0 an initial condition, thinking of time as starting, say, at t equals 0. And the differential equation, together with a specified value for this initial condition, is called an initial value problem. So the differential equation For this particular example, it suffices to provide that one initial condition, and that will give us a unique solution. In other cases, we will need more initial conditions. And these initial conditions don't have to apply when t equals 0. In some cases, we might specify values of x of t for different values of t. We could still call those initial conditions. We might be a little more likely to call them, use the more general term, boundary conditions. But many of the problems that we're going to be looking at in this course are of the form of initial value problems. Okay, so as I said, we could think of x as representing a population. In which case it would model the case where there are no particular limits to growth, where there's plenty of food and shelter, and so on. And in such cases, we do tend to observe exponential growth. I guess another example would be a pandemic. In a case where much of the population has no immunity to the infectious agent, in such a case you would expect to see exponential growth unless people take action to reduce the value of this constant A here. That's what all of this physical distancing and so on is all about. Reducing the rate at which the number of infections grows in proportion to the population. So what if instead we do have limits to growth? Presumably, if your population goes on exploding exponentially, eventually people are going to start finding it harder to find food and shelter, or animals, or whatever population we're talking about. So what if there are limits to growth? Well, probably the simplest way of modifying this equation we've been looking at in such a way that you do capture this kind of limiting phenomenon is just to add another term to the right-hand side. So let's suppose we consider the case where dx by dt, or we'll often denote time derivatives using dots. So x dot will stand for dx by dt, the first derivative of x with respect to t. X double dot will stand for the second derivative of x with respect to t, and so on. So what if our x dot is equal not just to ax, but what if we add another term that's not in x, but say in x squared? So this additional term should be negligible when x is small. If x is small, then x squared is going to be really small, if you like. But as x becomes large, this second term will become important. So let's suppose that that initially x is, let's say, small. I guess I should try to quantify what I mean. We want this second term to be small in relation to the first. In other words, we want bx squared to be small compared to ax, or we could say we want bx to be small in comparison to a. So let's say then that x is much smaller than a over b. So at time 0, x is much smaller than a over b. How big might we expect x to get? Presumably, as x gets larger and larger, this second term is going to get more and more important, and that's going to decrease the rate of growth of the population. So how big can x grow? Well, presumably there will come a point at which the right-hand side of the equation becomes 0 and the population stops growing. When do we get that? Ax minus bx squared equals 0 if and only if we're considering positive values of x here. Okay. Positive values of x, so this is the case if and only if a minus bx equals 0. Or in other words, if and only if x equals a over b. So when x becomes equal to a over b, the rate of population growth will stop. Okay? So presumably this value, a over b, represents a kind of asymptote that x will approach. X will start out growing exponentially if initially x is much smaller than a over b. So this second term is very small compared to a of x. So we should essentially have exponential growth around the time t equals 0, but as x gets bigger and bigger, that growth should level off, and we should expect to approach an asymptote at x equals a over b. So let's see what we get when we actually find the solution of this differential equation, or the solutions. Turns out that this equation is also relatively easy to solve. Let's try to do the same thing as before. We have dx by dt equals ax minus bx squared. So we can again rearrange this equation and perform what we call separation of variables, making all the x's appear on the left-hand side of the equal sign and all the t's on the right-hand side. Again, you can't always do this for every differential equation, but in this case we can. So in particular, we can write dx over ax minus bx squared equals dt. Okay. So now we should simply be able to integrate both sides of the equation and get an algebraic equation relating x to t. How are we going to integrate the left-hand side? Well, this looks like a good candidate for using the method of partial fractions. And let's go through this exercise because we're going to be using partial fractions quite a bit later on in the course. The idea is that we want to rewrite 1 over ax minus bx squared as factoring the denominator 1 over x times a minus bx. Okay. And this we can rewrite in the form, say, of some constant capital A over x plus another constant capital B over a minus bx. We just have to find the values of these constants a and b. Okay. How do we find these values? Well, an easy way to do it is the so-called Heaviside cover-up method. So let me just rewrite the equation like this. 1 over x times a minus bx, we want to decompose into partial fractions like this. So if we wish to find a, obviously the algebraic way to do that would be to multiply both sides of the equation by x, and then we'd want to solve for a. But an easy way to solve for a would be noting that if we multiply through by f, what do we get? By x rather, what do we get? The x disappears from that denominator, and we get an x in the numerator of the other terms. Now on the left-hand side, the x's cancel out, so we're in fact just left with 1 as the numerator. On the right-hand side, the x remains in the numerator. So we can make our equation relatively easy to solve by simply setting x equal to 0. And in general, what we're going to be doing is taking the denominator that appears under a, which in this case happens to be x, multiplying through by it and setting that value equal to 0. That will make the other terms in our expansion, just as in this example, vanish, and that will make it easy to solve for the constant a. At least that's the way it works out in this simple case, where the factors of the denominator, x times a minus bx, are distinct. This is called the Heaviside cover-up method for the following reason. Just let me write out the equation again, and this should become clearer. We had 1 over x times a minus bx equals a over x plus b over a minus bx. Okay, now again, the algebra is that we multiply through by this x, and then we set x equal to 0. That's going to make this term vanish, we know that, so we really just have to evaluate this term, what happens to this term when we multiply through by x and then set x equal to 0. Well, you can picture what you get when you multiply through by x by covering up this factor x. If we multiply through by x, it's just going to make that factor x disappear. So cover that up and then set x to 0. This will just give you 1 over little a. So by Heaviside cover-up, the Heaviside cover-up method, we have a equals 1 over little a. And then we can do the same thing to evaluate capital B. In that case, we're going to multiply through by this denominator, a minus bx. Okay. And then we're going to set a minus bx equal to 0. In other words, we will set x equal to a over b. That will mean that this term will disappear because it'll be multiplied by a minus bx, which is going to vanish. And what will we be left with? Well, when we multiply this left-hand side by a minus bx, that's what we get by covering up this term. And then again, we're going to set x equal to a over b. So this is just going to give us b over a. So we can see pretty easily by following this cover-up method that capital A has to have the value 1 over a, and capital B has to have the value b over a. So finally, our partial fractions decomposition lets us rewrite 1 over x times a minus bx as 1 over a divided by x plus b over a divided by a minus bx. So this decomposition will make it a lot easier to perform our integration with respect to x. So we saw that we could perform a separation of variables, getting all the x's on the left-hand side of the equation and all the t's on the right-hand side. If we now apply our partial fractions decomposition to the left-hand side, which depended on x, we find that the integral of the left-hand side is the integral of 1 over a over x plus the integral of b over a over a minus bx. And that has to be equal to the integral of dt. Again, we're talking about indefinite integrals here. Okay. So again, when we perform this integration, we're going to get constants of integration showing up. I'm just going to go ahead and lump them into a single constant. So what does this give us? This will give us, I should probably have said before, we were assuming that A is positive. We're also assuming that B is positive. So what are we going to get? We're going to get 1 over A times the ln of the absolute value of x plus B over A times the ln of the absolute value of a minus bx. Okay. And that's going to be equal to the integral of dt, which is t, and then taking all of the constants of integration into account, we can lump them together into one constant c1. Oh, sorry, I haven't done this quite right here because this is a bx here. So in fact, we need a factor minus 1 over b here. So performing the integration properly, we get minus 1 over b times this term. Okay. So what this gives us is 1 over a times ln of the absolute value of x minus ln of the absolute value of a minus bx. So that gives us ln of the absolute value of x over the absolute value of a minus bx. And that has to be equal to t plus our constant of integration. In other words, we must have that ln of the absolute value of x over the absolute value of a minus bx is equal to at plus a second constant c2, which is obviously just a times c1. Okay. Okay, so suppose, as we said before, suppose that we're considering values of x that lie between 0 and a over b. Then both of these terms within the absolute value signs will in fact be positive. So we're just taking the ln of x over a minus bx on the left-hand side. So using exponentiation, we get that x over a minus bx equals some third constant, say c3, times e to the at. So in this case, our c3 is just e to the power c2. And again, this c2 was just a times c1. Okay. So in other words, this still isn't a very nice solution for x. We can rewrite this as x equals c3e to the at times a minus bx. And then solving for x, we can get that x is a over b times 1 over 1 plus a constant c times e to the minus at. Now, what happens if we plug in T naught here? Suppose that e to the a T naught equals this constant c. Then when t is equal to T naught, this second term in the denominator is going to be equal to 1. So if we assume, in other words, that T naught is equal to the ln of c divided by a, in that case we can rewrite this as x equals a over b times 1 over 1 plus e to the minus a times t minus T naught. And that is what the solutions of our equation look like. In this case, we've applied an initial condition at time t0. We've just let t0 be the time at which this equality holds. And then instead of just having a constant c, we can have this expression in T naught. That's just a different way of writing out our original solution, which we had up here. This is a common form in which to write out this function. This is called, well, the equation that we've solved, the differential equation that we've just solved is called the logistic equation. Differential equation, or diff-EQ. And the solution, x of t, is called the logistic curve. Now, there's a plot of the logistic curve in the notes, which is probably a lot neater than anything I will be able to draw here, but I'll give it a try. So here's our t-axis. Suppose we're going to plot x on the vertical axis, but actually we'll also plot some derivatives of x. We reasoned earlier that there was going to be an asymptote at a over b because x dot has to equal 0 if x ever becomes equal to a over b. So if we start out with an initial value of x that is between 0, so this will be x equals 0 and t equals 0. If we start out with an initial value of x that's between 0 and a over b, then initially we will have approximately exponential growth. But that growth is going to level off as we approach a over b, and if you plot this function you get something looking like this. the time t0, what happens if t is equal to t0, if we go back and look at our expression, if t is equal to t0, we'll get 0 in the exponent of this exponential. So this will be equal to 1. So x itself will be equal to 1/2 of a over b. Okay, so we will be halfway between 0 and our asymptote at a over b when t is equal to t0. So as you would expect, if you plot the first derivative of this logistic curve, it has a peak when t is equal to t0. So it looks something like this. Let's see. So this is the first derivative of x of t, which we often denote x dot. And in the notes, the second derivative is also plotted. So this is a case where if, say, x represents the growth of the population, in this case our differential equation models the fact that there are probably some limits to growth. It's about the simplest possible way to modify our earlier differential equation, which was just dx by dt equals ax. All we've done has been to add a quadratic term in x to the linear term ax that we had earlier. That's sort of the simplest way to generalize that earlier equation. We've written it as minus bx squared, assuming that b is positive, and that gives us this kind of behavior which does indeed model growth with limits. And this is used to model various situations. Such as growth of a population. It can also be used, for instance, to model resource depletion. So there's a little discussion in the notes, which I won't go through here, about the idea of peak oil and how fitting a logistic curve like this to the data on oil production in the US was used to predict the time at which the production of conventional oil would peak. Which is sometimes referred to as peak oil. This can be used to model various phenomena. So those are just a couple of examples. Again, the first one, dx by dt equals ax, gives you exponential growth when a is positive. Of course, if a had been negative, it would have given us a decaying exponential. Okay. And again, that's a simple example, this about one of the simplest possible examples of a linear differential equation with constant coefficients. That's the kind of equation that we're going to be focusing on in this course. This second example, where we added minus bx squared to the right-hand side, obviously that gave us an equation which we're going to call nonlinear, because the minus bx squared is a nonlinear term. So the main techniques that we're going to study in this course will not give us a general way of solving nonlinear equations. In fact, there is no general way of solving all nonlinear differential equations. Nevertheless, when faced with a particular nonlinear differential equation, one can often find a way of solving it. It's a bit like trying to integrate functions analytically. You can't do it in every case, but often if you're clever enough, you can find a way when you're confronted with a specific problem. So that concludes our first two examples, and I think we'll stop this video there. It's been a little while. These two examples have been kind of typical in the sense that the independent variable with respect to which we do the differentiation in order to get the derivatives in the equation it has represented time, t. That's very common in applications of differential equations, but our next example will look at will be one where the independent variable is a spatial variable and where time doesn't enter into the picture at all. So I'll see you then in the next video to look at that example.